So hello, welcome to Econometrics Melody. This video is about the binomial distribution. We'll talk about the binomial distribution. First, the essential ingredients and some of the basic ingredients: exponential and logarithm. They are inverse to each other. That is what the result we're going to get is simply a factorial of this value. So factorial from 0 to 6. They are displayed 0, 1, and so on. They are very simple. Factorial of 2 is 6, and factorial of 3 is factorial of 2 is 2, factorial of 3 is 6, factorial of 4 is 24, factorial of 5 is 120, and factorial of 6 is 720. They are simple. This is how we can calculate the factorial in a Stata. Similarly, for this number 30, if we want to calculate the factorial of 30, we get this big number. Another useful function that we require in binomial distribution is combination. And how do we explain this? So let us run them first and then explain. So there are one ways to calculate, to extract nothing out of three objects, and there are three unique ways to select one object out of three objects, and there are 120 unique ways to select three objects out of 10 objects from 10 objects, and there are 6,435 unique ways to select 7 objects out of or from 15 objects, and there are 167,960 unique ways we can draw 9 objects from 20 objects. Now let us look at the binomial function, the formula of the binomial function or binomial distribution, and for any binomial outcomes, the probability of success p, that itself is the mean, and the variance is p into 1 minus p, the product of probability of success and the probability of failure, that gives the variance for any boundary outcomes. And if we multiply by n for n number of trials, the mean is np and the variance is np 1 minus p. So in order to calculate the probability of certain success, case success, we use this formula: combination of n out of n trials. What is the probability of getting case success? So we take the multiply this combination by probability of success to the power number of successful trials into failures into number of failure trials. And if we want the cumulative distribution function, and if we want k or less success, as for example 6 or less success, then we sum the probability from 0 success all the way to k success, and we will see it by the help of example. And this is going to be a very simple example. So let us calculate the cumulative distribution function, and Stata provides this function binomial to calculate the cumulative distribution function of binomial distribution. And first example, we're going to calculate the probability of 0 success out of 10 trials when the probability of success is 30%, and this yields a very simple result, and it is 3%, nearly 3%. Now let us use the formula, the real formula: combination of out of 10 trials we want 0 success, and the probability of success is 30% to the power 0 success, and the probability of failure to the power number of failures. So this ensures the probability of 0 or less success. And let us see whether the value is same or different. Yeah, both of the values are the same. We run it together and we'll see they are one and the same. Now let us check, and this is a user written program, binomial CDF, and this will depict the cumulative distribution function. So after 10 trials, the probability of success is 30%, and let us see whether it is 3%, nearly 3% or not. For 0 success, it is nearly 3%. Fine, and we see this ladder kind of graph. So this depicts that the binomial distribution is a discrete distribution. So for 0 success we get this probability, and in between 0 and 1 we get the same, the probability value is same, and for 1 the probability of 1 or less, the probability of success is this value, and so on. Now let us reinforce the concept, and let us see another example. What is the probability of ensuring 3 or less success out of 10 trials when the probability of success this time is 50%? It has increased from 30% to 50%. And let us see what does it look like. it is 17.18%. And in order to ensure 3 or less success, it is obvious we add from 0, 1, 2, and 3 success, and we can get the probability of ensuring at least 3 or less success. So it should be 17.18%. That's fine. And let us see it by the help of a graph. Again, binomial CDF is a user written program, and 3 or less success, it should be 17.18%, and which is what we get over here. And we can always provide any other inputs. The number of trials in this case is 12, and the probability of success is 65%. Now the probability of success has increased. So let us see what will be the nature of the graph. The graph probability of number of trials is 12, probability of success is 65. So the mean should be product of this 7.8. So the graph is centered somewhere at 7.8 over here at this point, 7.8. And this latter graph, it represents that the binomial distribution is a discrete distribution. Now let us calculate the probability mass function and for the same values. So this binomial p, this is the Stata function in order to calculate the probability mass function for the binomial distribution, and the arguments are we need to supply n, number of success, and the probability of success. So we are again ensuring 0 success out of 10 trials when the probability of success is 30%. Again, it should be somewhere 3%. Combination of n, same, let us use the real formula, combination of nk and the probability of success p to the power k into 1 minus p to the power n minus k. But this should also, both of them should yield the same result, and it's again 3%. Now let us reinforce it by the help of the graph, and let us say it in the graph. Binomial PDF is a user written program. We have written it to depict the probability mass function of a binomial distribution for the arguments n and probability of success. Let us see what does it look like. It is this graph. At the backdrop, we have a normal distribution with the mean and variance equal to the binomial distribution that is at the forefront. And the probability of 0 or less success, it's nearly 3%, and that's fine. That's fine. We're inching very close to it. Let us see another example. Now this time the probability, we need three success out of 10 trials, and when the probability of success is 50%, the probability of success has increased. So the value, let us see what is the value. The value has also increased, and this is the formula. This is the typical formula. Combination of 3 success out of 10 trials, probability of success into the number of success we require, number of successful trials, probability of failures into the number of failures. Both of them should yield the same result, and let us say they are both 11.718% or 11.7185% or 11%. Now let us see it by the help of the graph, binomial PDF. So 3 or less, it should be somewhat 11%. 10 and 11%, that's fine. And we can always provide any other inputs like 12, the number of trials are 12, and the probability of success is 65. And let us see what does it look like. The graph should be centered at 7.8, somewhere over here at this point. Compare it with the normal graph, normal distribution graph at the backdrop, we see this result. Now let us draw the graph. Actually, draw the binomial graph, binomial distribution. So here, this is again a user-written program, binomial PDF one. It draws the PMF graph. So when the number of trials is 10 and probability of success is 30%, it draws the probability for each success value ranging from 0 to 10. And let us see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is it. This is how we get the PMF, probability mass function graph, probability mass function of the binomial distribution. And let us do it once again, and this time we're going to actually, we see the probability, the x value 0 success all the way to 10 success and its corresponding probability, and when we draw them, so this is x against y, and we get that binomial distribution. Well, let us again say binomial PD of 10 and 5, and this time we're going to connect it by a connected line, and it will give us a feel of a histogram that we have, and it draws it against the binomial graph. This is what we're going to get. So when the probability of success is 50%, 10 trials, so the graph should be centered at 5, and this is what we see. And this seems to be more symmetric when the probability of success is 50%. Now let us track the changes for across all the probabilities, and let us see, we'll draw the binomial distribution for certain probabilities. Let's say probability of success is 0, this is 10, and so on. For different probability of success, what does the nature of the distribution look like? And at 50% probability of success, 50%, the graph is more symmetric. 60%, and as the probability of success increases, the left tail will increase. Now let us track this change for across probabilities, and we'll draw the graphs in a single graph. We'll draw them in a single graph. Probability of success 15%, 25%, and as the probability of success reaches nearly 50%, the graphs is more symmetric, or they get a bell-shaped curve. 74%, and so on. So for this 45%, the fourth one, 5, 15, 25, 35, 45, and 55, they seem to be more symmetric. And for large number of n, irrespective of the probability of success, the graph seems to be bell-shaped. It tends to coincide with the normal distribution. The graph at the backdrop, it represents the normal distribution, and the graph with the red line, or this layer graph, it represents the binomial distribution. The number of trials is 100, and the probability of success is 90%. So to some extent, it seems to be coinciding. Now let us track the changes when across the probabilities, and let us see when the number of number of trials is 300, and let us see, they appear to be the bell-shaped curve. 20%, 30%. So irrespective of the probabilities, the graph are bell-shaped in nature, or they actually coincide with the normal distribution. At the backdrop with the mint, we have a normal distribution. Now let's draw the graphs, the same graph, and we see it for the middle area, and this is what we look like. It represents the bell-shaped curve. Across the probabilities, if you notice, for different probabilities, the nature of the graph is a bell-shaped. When the number of trials it is infinitely large, or for large enough, then the nature of the graph is a bell-shaped curve. Actually, in fact, it coincides with the normal distribution for the given mean and standard deviation. Now let us see graph area. This is useful for the hypothesis testing, and let us see what happened for certain score. Here it's let's say 9, and what is the area? This is the binomial. At the backdrop, we have a normal distribution with the same mean and variance to that of the binomial distribution, and we want to test. This is useful for the hypothesis testing. And what is the probability of k being less than or equal to 9? So this red line, dotted line, it represents 9. And what is the probability of being less than 9? It's 95%, and greater than 9, it's 11%. So for the null hypothesis, we assume that the probability is 30%. So this binomial distribution is when the probability of success is 30% for n 20 trials, and for these outcomes. Based on our alternative or null alternative hypothesis, or based on our situation, we test the hypothesis. But in this case, both less and the greater condition, or the alternative hypothesis, both the alternative hypothesis, they are rejected. For the null hypothesis, we have the probability of success being 30%, and we cannot ignore. So this is the probability. Both the probabilities are less than, greater than 5%, way greater than 5%, way more greater than 5%. We fail to reject the null hypothesis. And this is all again a user written program, and we can manipulate its number of trials as well as the value of observed k, that is the number of success, and the assumed probability. So let us, for these parameters also, let us draw our binomial distribution. Now what would you say? So if again our null hypothesis is that the probability of success is 30%, and for this null hypothesis, let us test the alternative hypothesis. If k is less than or equal to 12, so we fail to reject the null hypothesis because it's 99%, 87% of this area is covered, included. If the alternative hypothesis is greater than 12, because the area is greater than 12, the area away from this 12, borderline 12, is actually less than 5%. So we can say that this k is greater than or equal to 12, actually that does not belong to this region because it's a almost zero. So in this case, we reject the null hypothesis. This portion may not belong to this region. This is what the basics of the alternative hypothesis. And let us check the hypothesis. Now let us display what are the list of the variables that we have, and then let us tabulate body, and then again tabulate body. So binomial variable, fat and thin. Body is actually a binomial variable with the binomial outcomes, binary outcomes, fat and thin. And let us say 0 is for represents fat and 1 represents thin. Now we want to see, yeah, the frequency for thin, there are 95%, 95 people they were thin, and its corresponding probability is 31.67%, and we want to test whether the 30% of the people are thin. This is what we are going to do, and let us see what happens. And our alternative hypothesis, and for the corresponding values, let us draw that area graph that we have just drawn, and let us keep these values in mind. K is greater than or equal to 95, we have 28%, nearly 40%, and less than or equal to 95, it's 75%. And let us say this value, corresponding values, less than or equal to 95, we have 75%, 75, and greater than or equal to 95, it's 28. So this 95, the red dotted line is represents the 95, and less than it, the area is 75% of the area, and greater than it, it's 28%. So in either of the cases, we fail to reject the null. So we can say that normally 30% people are thin. Let us see another example. Display binomial. So what is the value of it? It's 12.18, and only one success out of 9 trials. So it's 12% of the time. Now let us check the hypothesis, and let us first of all depict it in our graph. So k is less than or equal to 1, the area is 12%, and k is greater than or equal to 1, it's 97% and 12%. So both of the areas, they are greater than 5%. This is 12% and another is 97%. So we fail to reject the null in this case, and we can say that AP, the probability is 35%. This is true. We fail to reject the null. And let us again use our immediate inputs. Let us say there are for 50 trials, the actual probability of success is 40%, and can we claim that the probability of success is actually in fact 95%? And let us say what is the result like. So let us see these values. It's 1% and 99% for these figures. And again, it's let us say the detailed one, opposite extreme, it's again less than or equal. until test, and it's 1 and 99%. And let us see whether we get the same values or not. It's nearly 1.39 and 99, 99.37, 1.39, 99, 1.39, 97. So this is the picture. This is the graphical depiction of that situation. So for less than, it covers 99% of the area. So we assume that the null is true. We are assuming that, okay, the probability of success is 25%, and we draw this graph, and this graph represents the null hypothesis. So whether we are able to reject the null hypothesis or we fail to reject the null hypothesis. So let us see the alternate one. For this alternate, it's 99%. So we fail to reject the null hypothesis if our alternative hypothesis in this case is less than or equal to 20. But if our alternative hypothesis is greater than or equal to 20, then is the probability, or is this value is less than 5%, and we can say that this region may not belong to this graph. Region marked by yellow color will not belong to this region. That is why if our alternative hypothesis, if we are testing our null hypothesis against this alternative hypothesis greater than or equal to 20, then we can reject that this area may not belong to this null region. It's less than 5%. In this case, we reject the null and we favor alternative, and k is in fact greater than 20. But if for anything less than it, we say that the entire region is on behalf of the null hypothesis. It favors the null hypothesis 99% of the time. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.